thank you, Jim, for introduction. This is a very special occasion for me because I just remember that I think my very first talk in the IAS was given 10 years, 10 years ago, at the 70th birthday of Bob Langlands, and he was named 40 years of Alpha of L group, right? Yes, it's okay. And so happy birthday, Bob, and I hope that you keep being its impressed one for the next 80 years to come. Okay. So well, I mean, I don't have much of a concrete reason to report, but I do guess I think I've been working on this project on the endoscopy for a couple of years now, and what I'm trying to say, it seemed to me that maybe there's some some realistic way to approach it. So, but first, let me inspire you on this. I just try to recall some basic things to put things into context. So so you're all interested in this Langlands functorial conjectures. So it is about when you have two group H and G, reductive group defined over some global field. F given with homomorphisms between the dual groups, then you expect there's a way to transfer automorphic representations. So automorphic representation of automorphic representation of G. So actually not quite automorphic representation of G, but the packet of them, because there's more of the So I'm not going to emphasize the importance of it because I'm pretty sure that you're all convinced about it. So let me just mention one of the small but important case of functoriality that is basically known now, the endoscopic case. It's about basically when LH is more or less the centralizer of a semi-simple element. Of Lj, so is the final product of cumulative work for almost 40 years, many people. It's based on the trace formulas built essentially by Jim Arthur, and also on the transfer and the fundamental lemma, which was Vansberger and Truman also contribute something. Okay, so this case is especially important because one side it give a kind of precise and what packet means. So it have to state the conjectures in a more precise way with multiplicity formula and so on. But also what has been, I think Bob has insisted on is it would give you a stable trace formula. which should be a basic tool you want to use to when you work on the general scale functorialities. realities. So around 2000, maybe a little bit later, Langlands proposed a new approach to general functorialities, so he termed it beyond endoscopy. Which is some kind of new radical new way of using a stable trace formula to with I into the isolating the part of automorphic spectrum coming from a smaller group via functorialities. So so in this so new breed of stable trace formula, and on the spectrum side, that should look something some on the sum of orbital integrons. On the geometric side, as usual, but on the maybe a limit. On the spectrum side, it should be something like a sum of logarithmic derivative of L function. So one can attempt to use to look at the points of these I mean the residues of the right-hand side to have information about all the point L function, and therefore to isolate the part of automorphic spectrum that come from H. And there is also another variant that was of the same the same order of idea is to build trace formula with instead of D log just L function instead. And so for my today talk, I'm not concerned with this approach, try to isolate the automorphic spectrum coming from functorialities, but actually on the use of this formula. This is kind of formula. I mean, I'm not trying to make more precise later, but a kind of new stable trace formula with the on the spectrum side some L function to to as an approach to the general functorialities. Okay. So let me say a word about these automorphic L functions. So it's come from very early in the one of these revolutionary papers of Langlands on problem automorphic forms, when he constructed general automorphic L functions. Now we start with G, and with the representation of finite dimensional representation of the L group. Then for every automorphic forms, representation of G, you build the, I will write like this, L of S pi as Euler product of right, and so this is convergent for this Euler product is convergent for when real property of the complex parameter S is greater than something, and we want to prove that this Euler product can be meromorphic continued and has satisfied functional equations similar to the Riemann zeta functions. So the question is the meromorphic continuation and functional equation. This is the question. And one case that for all this is known is standard case. Is when G is Gn len and rho is the standard representation. And then all this is known due to works by first by Tamagawa and then by Goldman-Jacquet. So if you admit functorialities, so the functorialities would imply this. Let me call this standard properties of L functions imply the standard properties of automorphic L functions, because basically by functoriality you reduce everything to the case of standard case, right? Every automorphic L function would be standard L function, right? And if I'm not mistaken, the opposite is essentially true. That is converse theorem. If you know everything about automorphic L functions, then you would be able to have functorialities in some form. I'm not sure how much precisely we know, but I guess this is the expected. And so, I mean, in some loosely speaking, you can say that functoriality is equivalent to the standard properties of L functions.
The converse you need
So
meromorphic is not enough.
functional equation.
Meromorphic is not enough. You need actually to know what the fault is. You need entire.
Okay.
I'm just
No, I'm not saying that it is I have to put quotation mark here. Okay.
Functoriality will give you all you need.
Sorry?
I'm asking a question to Peter.
Yes.
He says you need more to get back.
Yeah, you need
You
much
get
more
more in the other direction too.
Oh, okay.
Functoriality doesn't.
Okay. Okay. So so almost at the same time as the endoscopy papers of Langlands, there was another approach to general case, but for the functional equation that was proposed by Braverman and Kashdan. So he proposed a way to to prove standard property L function in general. So and it just it's just a generalization of Goldman-Jacquet method. So in order to talk about Braverman-Kashdan, I just just recall you very briefly what Goldman-Jacquet is about. That make it easier to talk about the Braverman-Kashdan set of conjectures. So to the standard case. So G equals Gn len and rho is standard representations. So this is based on the so let locally. So you have the Gn len of Fv, if V is non-Archimedean place, and the main heroes, it is called the Schwarz space, and here is the space of locally constant. functions with compact support on the space of matrices. So I just denote it by M standard. And M standard is so G, G, and N. And M standard is the space of matrices, N by N matrices, right? So in this case, you can do the zeta integrons. So you can use the zeta integrons. And phi is so for AV pi representation of GFV, you can do zeta integrons like in TET series. So this is very much more or less straightforward TET series. So phi in the Schwarz space. So F is a metric coefficient. A pi and S is complex parameters. And look at this function and look at the common denominators. And that gives you rise to your N S pi standard. And the main ingredient to make this thing work is the Fourier transforms. So now, because we are working a function on vector space, space of matrices, we have the Fourier transforms. Fourier transforms is operators from the Schwarz space itself. So let me consider standard everywhere. And when you look at the zeta, what you get is a very nice formula. Just change the Fourier transform of phi, and then you switch F to F check. F check of G is F of G minus 1, and 1 minus S, and I don't know plus or minus, but N minus 1 over 2 plus or minus 1 is the same as Phi F S, and then there's the gamma factors. So this gamma, so the whole point that the gamma factors is doesn't depend either on phi nor on F, but just on pi itself. And so this, and then the so somehow, I mean, in some term, the gamma factors is the Mellin transform of the kernel of the Fourier transforms, right? And globally, we have that the product of over on if pi v is automorphic, then if that have a product of gamma S by V is 1 over on places, and that can be derived from the Poisson summation formula. On the space of matrices, so there's a vector space, you have the Poisson summation formula. Okay. So now, so what by Mann-Kazan proposed, I can actually do the same story for general case. So for every G, every row, it should be able to construct a a space, a Schwarz space S rho, depending on rho, a function on GFV. Now it's no longer this, so of course this is no longer true. You don't know how to define it yet. So that should exist. This space of functions.
So one problem, I assume, is where you had n by n matrices and Poisson summation on a linear structure.
Yeah, I'm going to come to this. Yeah. And we should have the Fourier kind of exotic Fourier transforms, a non-standard Fourier transform on that space that map the rho Schwarz space to itself, so that you still have this kind of local functional equation. So this gamma, this gamma S pi, and it should have this this formula, right? So that I mean, so yes. So okay. So as Peter pointed out, the main difficulty here is, I mean, this basically is, in general, you have here we have use the rho some kind of extraneous data that is a space of matrices that have this, you can add, right? Addition, and then you have Fourier transforms. So now, so the point is that actually maybe you can still do without it. So first of all, you need to understand what should replace the space of matrices. So first of all, there is some very some very basic confusion. Is talking matrices should be the Lie algebra of GNLN, but obviously this is not, because here you really use the fact that the GNLN is G is inside M standard, right? Because you define Schwarz L function, S function on G that can be extended as locally constant from the compact support the matrices. So obviously here M is not Lie algebra. So in general, what we want to be M rho is, I mean, you can just list the, I mean, for the first thing you should see that M rho should be algebraic varieties. Maybe for the first to have normal of phi, algebraic varieties containing G as an open subset, such that G times G, that accent of G times G on G by left and right translations extend to M. I mean, when you look on this integral, that is the basic requirement that you want to action to extend to your varieties. And this is actually some, you know, that I'm surprised that I didn't know it before, but this is it's called the reductive monoid. So this is what the other monoid. That was a theory that was developed kind of independent of everything else by people in Pucha, Renner, and Winberg. Right. So the reductive monoid, in one sentence, is a kind of combination of theory of reductive group, like in Boren book on one side, and toric variety on the other side. So
If I understand continuous vector spaces, they would be useful in this one.
homogeneous vector space.
That's where you have one, so that's a property that GLN might want.
No, but yeah. So that is both is inside some bigger things, but they are not connected. Yeah, it's spherical varieties, but yeah.
But you just say what a reductive monoid is?
So reductive monoid is a phi, normal a phi algebraic varieties, right, with the multiplication structures, monoid structures, so that the invertible element form an open subvariety which is a reductive group. Okay, and so.
So for if you take GSP, just mention GSP.
Yes.
So then you get the, if you look at the multiplicative symplectic group, then you just embed it into the cone of things where you allowed zero.
Yes.
So that's again, it's a singular variety.
Well, I mean, the basic thing that you want to think about the monoid is you look at representation of finite dimensional representation of not necessarily irreducible, can be reducible, and then you just take the closure in the space of endomorphism, and that gives you a monoid, and that is. So there is very nice, actually very, I mean, surprisingly nice description of reductive monoid is as follows. So if you have G in M, right? So M is reductive monoid. So again, it's normal of phi algebraic varieties with multiplications, and G is unit point. So that is invertible point, and it's open subset. Okay, and then look at the maximum torus of inside T in G, right? And look with the closures. So the closures is MT is closure. Well, I assume it is normal and so on. I mean, maybe it's that doesn't matter.
That depends on rho, some rho.
No, I come to rho later. Yeah. So let's forget about rho. Let's look at any reductive monoid, right? I try to classify them. And then I look at G, I look at the torus, I look at MT closures. And this is the toric varieties because it's just closure of a torus. And toric variety is given by some fan, right? So this is given by some strongly convex. Strongly convex rational cone. So something like this, right? So strongly convex, you don't want to have a line inside, right? Because it's supposed to be affine. And what you want is this cone, so this is NW equivalent cone because you have the Weyl group action, right? So basically, you want you look at the vector space of characters or co-characters. I mean, the real vector space of T, and you want a cone, strongly convex cone that is stable by Weyl group. So you already see that you cannot do it for semi-simple group because the Weyl group just move vector around and it just cannot have strongly convex cone to generate the whole vector space. So G has to be reductive, not semi-simple. And this kind of GM center is very essential to build monoid. So now come back to Bob's question. You can build, so the simplest monoid you can build is as follows. Simplest. So you want a GM. So what you actually do? Assume that G is have kind of determinant map to GM and maybe G prime. And you also assume that in dual side we have. So assume it's G split. So I don't want to care about Galois structures. Now. Just look at split things. So it is C star. And you assume that we have rho is a representation of G hat in G and V of rho. And we assume that the C star act by scalar multiplication. So that means the C star here, this is identity, right? So now just look at the, now we do have the, when you look at the space of this vector space of co-characters of T, real vector co-characters of T, then you have a cone. The cone just given by the weight of this. So it's something like this. So you have the levels given by the determinant, right? Right? And here is the weight of 0, and the second level is the weight of sim square of 0 and so on, right? And then you have a cone. And because you have this positive direction, that makes your cone is strictly convex. And then you have your torus. And that this I call the, then for now rho is irreducible. Right? Because when you talk about weight, when you talk about irreducible, I mean the non-irreducible is very interesting, but I still confused. But probably have to go away from here, some stucky stuff. But so now just stick to irreducible case. So they have this M rho. So this you have now algebraic varieties. M rho contain G. Right. Okay, unfortunately I erased the Bafferman-Kasdan proposal, but we want that so the M rho is going to play the role of the M standard in general. So when the standard K M rho is exactly the space of matrices. But the main, the first difficulty is in general, except standard case, M rho is always singular. So this is always singular. And when it's singular, it doesn't make sense to talk about smooth function anymore, right?
Say it again.
So X away from the standard case, the monoid M rho is always singular. Yes.
I didn't understand your definition of this fact. You take the
Con?
the cones generated by the weights of 0 and all symmetric power.
Yes, yes. And because because the determinant it's not on the so this the weight of the cone belongs to some affine space, not on the vector subspace. So okay.
The singularity is even present in the GON, or even in Riemann's case, you have to remove point. You always
Well, it is singularity in the other way, but the space, the space where the function identified is smooth, right?
Yeah.
So
He's compactifying the cone. The monoid adds points at infinity to your cone.
I don't know. I don't see it that way. So keep in mind, I shouldn't erase it, but the MT here is very important, historic varieties. It's not just a divide to construct a monoid, but you come back that the MT is going to be the space set echelon later, so just before I erase it. Okay, so now let's go back to the Schwarz space. So when rho is standard representation, then S standard is the space of locally constant functions with compact support in M standard. Right. Now in general, we don't know. It just, the basic guess.
I
think what was more or less implicit is in Barman Kasdan papers is it should be a function. It should be some kind of function with compact support on M rho Fv. So, I mean the non-compact support of this function become compact. I mean the closure become compact inside M rho. So the direction. I mean but it no longer makes sense talking about smooth function because the space itself is not smooth, right? So we need, but instead of that, we need to impose some intelligent conditions. So it's kind of asymptotic condition on the boundary. When I mean asymptotic condition, that means that the condition that define this space should be local, right? Local. That means this should be the space of compact support section of M rho Fv inside some sheaf. I mean, in some sheaf. So the sheaf would encode on this asymptotic condition. I don't know what it is, but I mean 100% should exist. Okay. So, but what we know, I mean, I do know now is something much smaller, but it's useful. Is in this case, I mean, as for the trace formula, so this will be the space, by the way, the test function for the trace formula, and we want to have two ingredients, a space of test function, but also one distinguished vectors, right? Like so in this has one distinguished vectors is the characteristic function of M standard O, the characteristic function of the integral matrices, right?
Excuse me, why do you say trace formula? I thought you're trying to just develop the meromorphic properties of the L function directly. I mean, Jacquet-Gourmand doesn't use trace formula.
But I try to use trace formula.
This is something you want to put into the trace formula.
I want to put in the trace formula in this.
But I assume Braverman and Kasdan were just trying to
To do, yes, that's right, yeah. So by the way, this function is the property that when you look at it trace on the unramified representations that give the unramified local L factors, right? Otherwise, it will give you 1. Well, in here I want to do the same function. So this let me call it basic function for beta for basic rho of V. So the function with the property that trace of trace of beta V rho on pi V. V is a representation of local used be the L factors L at some specific values. So in the Gourmand-Jacquet case would be this m minus 1 over 2. So this here is some numbers. I don't know. It's something like rows again the half sum of roots or something, yeah, of pi v, maybe a plus minus. I have it in my note, but I forget the sign. For when pi v is unramified and 0 otherwise, right? So we want this function. So this is going to be invariant on the left and the right by the maximum compact, right? So it's going to keen on the unramified representation, and you want to have these properties. And this you actually have very nice properties. This is the it is the you can prove that it is actually given by the IC. So we start from, so let briefly move to the function fin case. Even I think it is not a serious issue. So let Fv to be Fq of t and OV to be FQ of T. Then this space M rho of O become infinite dimension varieties over FQ. So we're going to the arc space of M rho is FV. And I claim that this the function that is defined by these properties is given by the singularity of this arc space. So this is the IC of L M rho, right? So this is the reason of run by Boutier, myself, and Sakellarides. Okay. Okay, so that is the first point. Now the second point is now in conjecture you really want to have this as rho, the whole space of functions, and I don't. Let me just put off some very optimistic conjectures. Is that there should be there is a canonical resolution of singularities of M rho, maybe M rho ds, so that the Schwarz space be the space that now is smooth and compact support functions. On M rho yes FV. Well, it seems to be. I mean, it's not just a wish. I mean, I think I checked somehow this with some small case, right? In the
What cases of GL2?
GN2 and SIM2, SIM3. I don't remember, but at least in that case, I can construct canonical resonance singularity of this. Sorry.
Sim3?
I think. I mean, I haven't do everything carefully, but the resonance singularity for every SIM and for GN2.
For every sim?
For every SIM, yeah, yes.
So it's a very simple asymptotic formula for GL2.
I mean, now I have to check together. I mean, if it works, but
Very simple formula.
yeah.
Amazingly simple.
Okay.
No, but it may fit in exactly with what you have.
I think the whole point is the in this theory that I didn't know very well before, this Pucha and Renner theory, that just not describe monoid, but it's describe also the functoriality between this monoid, the map between them, just given by some very simple recipe with cones. Because G2 cone is very simple, so you can know all the maps and just glue all these things together, you get a resolution. In general, it's much more messy. You have many more cones. So I get lost with a two-dimensional case. But okay, so so now I mean there's now let go to see what is this Fourier transform. So okay, maybe before we move Fourier transform, I just want to because I don't have 10 minutes left.
So you can continue this afternoon.
Okay, so let me say something about the trace formula. So now we have the for every place V, we have this new Schwarz space. I mean, we want to have GFV, and with one specific vectors beta V, beta rho of V, right? And with this, you can build the adelic Schwarz space. So that would be, you want to take the S is finite set, so then the SV, V in S, the rho of GFV, and take the limit, inductive limit on S, right? So it just tensor together finally many places, and then take limit. And the limit is defined because you have these specific vectors. So it's just like, I mean, concretely, it's just like a for V in S, you put the any function in the Schwarz space, and away from S, we have to put the basic function. Okay. So it's completely like in this. I mean, it's very similar to the usual case where this is the basic compact support function, and this is the Cartesian function of the integral point, and now you can build this. Of course, I have no idea what happened on the Archimedean place, but it would be very interesting to work out what's happening. And so, okay. So the trace formula that was alluded in Langland's papers, also paper with Hankel and myself, is we actually want to construct an invariant linear functional on this Schwarz space, right? So that is to see, right? So on the spectrum side, we just want to look at the trait of this function on automorphic representation, and it's just because of this, right? What we have here on the spectrum expansion is, I've just like a discrete sum that should be something like Ls of pi. Now S is always no more S because I put S to be this special new G again rows after I can translate. So it's only rho from here and pi, right? And orbital and the geometric side is of course just orbital integrons of F. The F is in this Schwarz space, right? Of course, and now I'm maybe a stable operator integrons, maybe a multiplicity, and then trace of product of V inside S, a trace of pi V and V. Okay. Okay, so. In this way, there is no limit process to be done. The limit process is with a lower derivative L function. Here, it's just a linear function on this. I mean, it had to have maybe hot function. Maybe you need to some other continuations, but it's just a trace. I mean, it's no longer it's just the linear form on some bigger some other vector space.
But you don't know it's
Where are you evaluating the L function?
Sorry.
I mean, the L functions, these L rows may have poles, right? So.
So far, I just writing formally. Yeah.
Right.
Okay. No, but I guess this is the kind of formula that just mean work on in some case at least. I mean, I strongly believe that this is. I mean, the problem is doable. I mean, it's nothing like logarithmic derivative. On the, I mean, I look at the geometric side more. I'm better geometric side.
With you more about not using the logarithmic derivative. That I agree with you.
But I mean, on the geometric side, I don't see any analytic problem very serious. I mean, it just look very much like the usual case. Okay. So I think that my time is actually over. So I would, well, if you allow.
We started a little bit late. Maybe if you want a couple of minutes.
So let me say, Xu Yang will not be able to attend the And Go is going to take up his hour later
Is,
this afternoon.
Well, just if you are not annoyed by this, but if you are, just say one word is so in Barman Kasdan proposal. He want they want to assume that this Fourier transform is defined, right? And then the Barman Kasdan proposal would be the sum over on G of f of now f is some local function, global function f of gamma equal to sum over the same thing of the Fourier transform of f of gamma with some local conditions, so that you don't have to worry about the boundaries, right? You have local condition. So this is the kind of non-linear Poisson summation formula that Barman Kasdan want to prove. I think that it may be more realistic actually to put something weaker, either just integrate the whole thing over GA mod GF, right? And in doing so, what you get is actually this, exactly this. I mean, up, and here you have on the left hand side you have the.
These are orbital integrals, are they on the left? X to the minus 1 gamma.
This is exactly the trace. I mean, this linear form. It's just the integration of this sum over the automorphic quotient. So it have both geometric expansion and spectral expansion. On the spectral expansion, what you get is sum of L functions, right? On the right hand side, you get exactly, if you're not mistaken, the symmetric L functions, right? So that is what you want to prove if you want to prove functional equation. And so, I mean, as you learn, you want to prove it by working on the similar formula on geometric side, right? So just basically you want to prove something like this. Right? Okay, so I mean, of course, you need to know more about what is F rho is to say something. But if you know, I talk about this afternoon. What